In the last video, we kind of scratched the surface of the most important word in all of Calculus 1, the derivative. Presumably that was a new vocabulary word to you when you started the last video, and hopefully by the end of the last video, you were able to make the connection between the derivative of a function and the rate of change of that function. Calculus 1 is devoted to this idea of the rate of change of a function. And generally, that's a really complicated thing to understand. However, if you're lucky enough to have a linear function, a function whose graph is just a straight line, well, because the graph is a straight line, the rate of change is the exact same. The steepness, which is a word we can use to kind of quantify the rate of change, is the exact same over here as it is over here. If you're walking up this hill from left to right, the hike is just as hard at this point as it is at this point, at this point, and at this point. The steepness is the exact same. The steepness of a linear function, its rate of change, is just constant. It's just the slope of the line. Unfortunately, Calculus 1 is not the study of the derivative of linear functions. It's the study of the derivative of all functions. So we need to move past these simple examples and into harder examples like this example right here. We again start out with a function, f of x equals 1/3 x squared minus x minus 2. Maybe if you were really good in a pre-calculus class, you'd be able to convert this equation into this graph, complete the square to write it into vertex form, apply function transformations. If any of that rings a bell, that's great, but frankly, if it doesn't, it's not that big of a deal. Maybe just trust me that this equation and this graph are two different ways to represent this function. In a pre-calculus class, you'd be asked a question like, evaluate f of 3. And hopefully in your pre-calculus class, you learned that really all this is asking you is what comes out of this machine, f of x, when I put 3 into the machine. And there's at least two different ways you can answer that question. The first one is algebraically, you copy exactly what you see here, except you change all the x's into 3's. So f of 3 would be equal to 1/3 times 3 squared minus 3 minus 2. And then simplifying this expression, let's see, 3 squared is 9, and 1/3 times 9 is 3. So I got 3 minus 3 minus 2. 3 minus 3 is 0, minus 2 more. Looks like I got negative 2. If I'm asked to evaluate f of 3, I could do it algebraically and figure out that the answer is negative 2. Or I could do it geometrically. If I was doing it geometrically, I'd understand that when I'm being asked to evaluate f of 3, I'm being told that the x coordinate is 3. Here's my x-axis. Here's where x equals 3. The height of this graph when x equals 3 appears to be negative 2. Therefore, f of 3 is equal to negative 2. I come up with the same answer. That's all great, and none of that is relevant because that's a pre-calculus thing. What we're interested in is not the height of the graph at this point. I can't emphasize that enough. We don't care how high this green dot is right here. What we care about is how steep is the graph at this point. We care about the derivative of this function, which is why you're being asked about f prime of 3 here, which is the rate of change of this function. Figuring that out is really hard. You shouldn't be able to figure out the rate of change of this function at this point. But maybe you learned enough from the previous video that you could figure out whether it's positive or negative, right? We don't know what f prime of 3 is equal to. It's some number. We don't know how to figure out that number yet. But will that number be a positive number or a negative number? Well, remember, f prime of 3 is asking you the question, at what rate is this function changing at this point 3? If you look at this function, maybe you can conclude that the rate of change is changing. If you're hiking this trail from left to right, over here you're going downhill really, really quickly, right? And then as you go further and further to the right, you're still going downhill, but not as quickly. Right over here, if you fall, you're sliding a long way. If you fall right here, no big deal. You get up and you just keep walking. You're going downhill. You get to some point somewhere in here and it's flat. You're not going uphill. You're not going downhill. Or maybe you eat lunch here or something. You've made it down to the bottom of the valley. You're feeling good about yourself. And now you start hiking out of the valley. And the start is really easy because we're not that steep. The slope of the trail is not that large of a number. But the further you go out here to the right, the steeper it gets. By the end, you're, rock climbing or whatever, getting up to the very top. We don't need to describe the rate of change at every single point on this graph, at least not yet. All we need to do is figure out the rate of change at this specific point right here. F prime of 3 is a question. The answer to that question is a number. My question to you, is that number a positive number or a negative number? If you're thinking that it's a positive number, that's fantastic. You're entirely right. How do I know it's a positive number? Because at this point, if we're hiking from left to right, we're going uphill. I know that's kind of weird and it doesn't feel concrete enough to be a concept in a math class, and frankly, it's not. But we don't have the machinery necessary to talk about this point more concretely. So for now, all I want you to see is that at this point, the derivative is some positive number. F prime of 3 is greater than 0. What if I asked you to compare f prime of 3 and f prime of 5? Could you tell me which of those two numbers is larger? If you're thinking that f prime of 5 would be larger, that's fantastic. Why? Because f prime of 5 is talking about the slope, big air quotes around that word, of the graph at this point. Why do I got to put air quotes around the word slope? Because slope is a word that's only defined for straight lines. And we don't have a straight line, we got a curve. So we can't really talk about the slope, but it's kind of the curved analog of slope that we're so interested in. If you can look at this graph and tell that the graph is steeper here than it is here, then you're understanding this idea of derivative. But maybe you're like, right, but I don't want to just compare two values. I want to know what is the derivative of this function at this point where x is equal to 3. I want to evaluate f prime of 3. I don't want to just compare it to some other number or say that it's a positive number. I want to know what the answer is. Okay, cool. I like that you want to know what the answer is, assuming that you do want to know what the answer is. The way we get there is by talking about what are called tangent lines. And to understand tangent lines, you really have to understand secant lines. Secant lines are a thing that hopefully you learn in your pre-calculus class, but maybe you did. But maybe a little review is in order. The idea with a secant line is it's always defined by 2 points. That's its defining characteristic. So if I wanted to talk about a secant line to this graph, if I wanted to, I don't know, sketch the secant line to f of x, I better be told 2 different points. So maybe the full prompt is to sketch the secant line to this graph f of x from x equals 3 to x equals 6. What is this question asking? Well, here's the point on my graph where x equals 3, and if I want to find the point on my graph where x equals 6, that's easy enough. Again, just locate on the x-axis 6, come up here, and figure out that the height of the graph is 4. I have these 2 different points. With 2 points, I can define my secant line. The secant line is just the line that goes through those 2 different points. Easy enough. Connect the 2 points with the line, and what I've done is I've sketched the secant line to this function f of x from x equals 3 to x equals 6. Done. Nice thing about the secant line is it's really easy to calculate the slope of a secant line. Why is it really easy? Well, to calculate a slope, you need 2 different points, and a secant line is defined by 2 different points. So the minute you have these 2 different points, you're a step away from figuring out the slope. This point has an x-coordinate of 3 and a y-coordinate of -2. This point has an x-coordinate of 6 and a y-coordinate of 4. And I know that the way that I figure out the slope, maybe you're thinking rise over run, is by taking the difference in the y-coordinates and dividing that by the difference in the x-coordinates. So if I call x1, y1, 3 and -2, then I'd call x2, y2, 6 and 4. Plug those into this formula up here. My slope is 4 minus -2 divided by 6 minus 3. 4 minus -2 is the same as 4 plus 2, which is 6. 6 minus 3 is 3. 6 divided by 3 is 2. The slope of the line connecting these 2 points is 2. Does that make sense? Yeah, absolutely it does. If we started at any point on this line, maybe this point right here, and went up 2 units and right 1 unit, we get to another point on the line. Up 2 more units, right 1 more unit, we get to this point. Up 2 more, right 1 more, it takes us to this point. The slope of the line connecting these 2 points, aka the slope of the secant line, is exactly 2. It's easy to figure out. It doesn't involve any new calculations that you didn't already know from a pre-calculus class or maybe even before that. As I work through this example, you might be like, yeah, I remember doing that. I did that in a pre-calculus class, but we had a different name for it. We didn't call it the slope of the secant line. We called it the average rate of change. Perfect. The secant line, which is defined by 2 points, gives you what's called the average rate of change, which is a major topic in a pre-calculus class. The reason you learn about the average rate of change in a pre-calculus class is it's a precursor to what we're going to be doing in a calculus class. In calculus, we don't care about secant lines. We don't care about the average rate of change. What we care about is the instantaneous rate of change, aka the derivative. And to figure out the instantaneous rate of change, you don't need to study secant lines. You instead need to study tangent lines. Tangent lines are similar to secant lines. I mean, they're lines, but their main difference, their defining characteristic is instead of being defined by 2 points, they're defined by a single point. And that's going to end up making them much more useful, but also much more complicated. So whereas the prompt for a secant line might ask you to sketch the secant line to some function f of x from x equals 3 to x equals 6, the prompt for a tangent line is going to look a little bit different. You're not going to be given 2 different points. You're just going to be given 1 point. Sketch the tangent line to f of x at x equals 3, not from x equals 3 to x equals 6. You only have 1 point. How are you going to sketch the line? Well, it's going to be a lot harder. X equals 3 corresponds with this point that we've seen a few times now. But how are you going to draw the line if you only have 1 point? A line is defined by 2 points, which is why sketching the secant line was so easy when we have 2 points. Tangent line is defined by 1 point, so sketching the line that's defined by 1 point is going to be a lot harder. Let me give you the answer and then try to explain what's going on. Pictured in red is the tangent line to this function at this point. It's a little bit hard to see, so maybe I can zoom in a little. There's a lot going on here, but completely ignore the green and completely ignore the blue. We're just looking at the function pictured in black and the line pictured in red. The goal is for you to be able to come up with the line pictured in red if I give you some function like the one you see pictured in black and 1 point. So what's going on here? Well, the easiest way to think about the tangent line is it's the line that just kind of touches the graph at a given point. The idea is we want a line whose slope represents the steepness of the curve at that point. So picture 2 different hikers. One hiker hiking along this black trail and one hiker hiking along this red trail. At this instant in time, those hikers are walking up equally steep paths. Earlier in their hike, like over here when x equals 2, the red hiker is working a lot harder than the black hiker. And later in their hike, like over here at x equals 4, the black hiker is working harder than the red hiker because this path is steeper than this path. But at this instant right here, when x is equal to 3, the steepness of the red path and the steepness of the black path is identical. That's the defining characteristic of the tangent line. The tangent line to a function at a point is the line that goes through that point and has the exact same steepness as the function at that point. It's pretty complicated. The way a lot of people think of it is, yeah, it's kind of the line that doesn't intersect this graph. It just sort of butts up against it. Well, yeah, that's true in this specific instance, but you got to be careful by saying it doesn't intersect with the graph. Consider this function g of x right here. Suppose I ask you to sketch the tangent line to this function at, I don't know, this point right here. What that tangent line would look like, roughly speaking, is something like what's pictured in red here. But note that this line in red intersects this graph in blue again down here. So I can't say that what the tangent line is the line that kind of touches the graph but doesn't intersect it, because in this case, the tangent line does intersect the graph later on. And you're like, yeah, okay, fine, but it doesn't intersect it locally. The intersection happens later. It crosses the graph later on here. At the point that I'm interested in, it kind of bumps up against the graph, but doesn't cross over the graph. Yeah, but even that definition won't work. Because think about what would happen if I tried to sketch the tangent line to this graph at, I don't know, this point right here. Because the graph is relatively flat right here, my tangent line is going to be relatively flat. But note that it doesn't just bump up against the graph, it kind of crosses from one side to the other. So as much as students want to, you can't really define the tangent line as a line that doesn't intersect the graph, although that idea is the right idea. We'll be able to define the tangent line more concretely when we learn more vocabulary, and I know that's been a common theme in these videos. But for now, I think the best that we can do for the tangent line is just think about it as the line that passes through a given point on a function whose steepness is identical to the steepness of the graph at that point. And frankly, even if you can't define it that concretely right now, that's totally fine. If you can sketch this line in red, or this line in red, or this line in green, if you were given the graphs either this one in black or this one in dark blue, and 1 point, this red dot or this green dot or this red dot, that's perfect. That's all you really need to know about tangent lines. Tangent lines are a little mysterious right now, and they're a lot more complicated than secant lines because of the fact that they're defined by a single point instead of 2 points. You may already see the punchline that to understand the derivative, if we want to calculate f prime of 3, what we need to do is figure out the slope of this line in red. We're interested in the steepness of the curve in black, but we don't have a way to measure steepness. If our function is linear, it's really easy because we can measure the steepness of a line, but if our function is nonlinear, then we're kind of stuck because we can't measure the steepness of a curve. So what do? We come up with a line whose steepness is the exact same as the steepness of the curve at a given point. This line represents the steepness of the curve when x is equal to 3. And then we measure the steepness of the line because that's something that we can do. It's just the slope of the line. What's the slope of the line pictured in red here? Well, we don't have the equation of the line in red, so the best we can do is kind of estimate it. It looks like we go up 1 unit each time we go to the right 1 unit. So it looks like the slope of this line in red is just equal to 1. Because the slope of the line in red is 1, and the steepness of the line in red and the steepness of the graph in black are identical at this point, what that means is that the steepness of the graph in black at this point is also 1. Therefore, f prime of 3 is equal to 1. To calculate derivatives, what we're going to have to do is understand tangent lines. Tangent lines are kind of like secant lines, except they're harder. What makes them harder is they're defined by one single point instead of 2 different points. But at this point in the class, if you can sketch a tangent line when given the function in 1 point, and then just estimate the steepness of that line, that's everything that you need to know how to do. And you might feel kind of uncomfortable doing that. I don't like estimating the steepness of a line. I'd like to be able to calculate it more concretely. Well, we'll be able to do that. We just don't know how yet. In fact, it'll be the next video when we learn how to do that. As a little preview to the next video, I want to leave you with one observation, this key fact right here, that secant lines and tangent lines are related. Specifically, secant lines, which are defined by 2 different points, turn into tangent lines when the 2 points get really, really close together. What am I talking about? Consider this line that we have in blue here. The 2 x values that define this point were x equals 3 and x equals 6. But what if we didn't use 3 and 6? What if instead I said to sketch the secant line to f of x from x equals 3 to, I don't know, x equals 3.1? It would be really hard to do because these 2 points are so close together, I'd have to zoom in really, really, really close. But maybe I could locate 3.1 on my x-axis somewhere in here, and then put a dot on this black curve with an x value of 3.1. Loosely speaking, I don't know, right here maybe. And then I could take these 2 dots, one in red and one in green, and connect them with a straight line. And if I connected this red dot and this green dot with a straight line, it would technically be a secant line because it's defined by 2 different points, but maybe you can see how it would line up really, really closely with this line that I've already drawn in red, which represents the tangent line. A key fact that will make more concrete as this section goes on is secant lines turn into tangent lines when the 2 points that define the secant line get arbitrarily close together. Secant lines approach tangent lines as the 2 points converge. This is a really powerful statement that we'll explore more closely in the next video.